All right. So I think that I'm live. Um, Hello, everyone. Bug says hi as well. Um, so today is the March 17th lesson for AP Physics 1. And so yesterday we talked about electric charge and we talked about the electric force. And so really that's all you need to know about the electrical force, what I talked about yesterday. Today, we're going to start to talk about electric circuits. Okay? So I'm just going to introduce the two basic quantities for electric circuits. So the first quantity is, actually, before I do that, let me just talk about two different classes of materials. So one class of material is called a conductor. And a conductor is, whoop, you guys can't see that. Let me scoot this over a little bit. A conductor is a material electrons can flow through easily. Okay. Then there's a material called an insulator, which is a material electrons cannot flow through easily. Okay. So these materials are actually different at the atomic level. So if we look at an insulator at the atomic level, let's say that these are the atomic nuclei. And for an insulator, the electrons that are orbiting the atomic nuclei are stuck around their individual nuclei. Okay? All right. So the electrons are stuck. Bug's falling asleep here. For a conductor, you have the nuclei, but the electrons are not stuck to their individual nuclei. The electrons are literally just flowing wherever they want to go throughout the material. So the electrons are not attached to their nuclei anymore. They can just go wherever they want to go. Okay? And in case you missed the news, I am monitoring the YouTube live stream. So if you have any questions, I see Ray's watching, Ava's watching, Daster the bear. I don't know who that is, but hello. All right. So these are conductors and insulators, okay? So we can sort of broadly classify materials in terms of conductors or insulators. Metals tend to be conductors. Things like rubber, wood are insulators, okay? All right, so let's suppose you have a conductor, all right? And a conductor, maybe here's a conductor. It's like a wire. Okay, and this conductor, okay, I'm going to set bug down. So this conductor is going to have charge flowing down it. So it's got all of these electrons that are flowing through it, the electrons. All right. Okay. And so there's this thing, it's called electric current. Electric current. And it's equal to the amount of charge that flowed divided by the time it took to flow. Okay? So the symbol for electric current is I. And so we could write electric current as charge over time. So it's the amount of charge that flows down this conductor divided by the time it took. So from this, it's pretty easy to get the units of electric current. The units of electric current would be units of charge divided by units of time. So I'll give you a second to think about what the units of current would be. And yeah, I think Kenny should be more original. I agree with you, Caitlin. So the units of electric current would be coulombs per second. Okay, coulombs per second. This has a special name. It is called the ampere, which is denoted by A. All right, so this is electric current. It's the amount of charge that flows through the wire divided by the time it took. So you could think about it intuitively as the rate of charge flow. Okay. Looks like Ray has an actual substantial question. Why are metals and water good conductors but not rubber or wood? That's an excellent question. So I'm going to address the water part of that. Pure water is actually an insulator. Salt water is a conductor. So why is salt water a conductor? Well, when you put salt into water, salt is sodium chloride. And when you put it into water, the sodium and the chloride separate from each other. And so you have floating charge in the water. So it's not, in salt water, it's not the water molecules themselves that conduct the current. It's the sodium and the chloride atoms that are floating around that are ionized. Those are conducting the electric current. Okay, so as far as why are metals good conductors, it turns out that if the lowest energy state of a metal is one where the electrons can go wherever they want. So all materials are trying to lower their energy to the lowest amount possible. And for metals, the lowest energy state is for the electrons to be able to go wherever they want. So that's what they do. But for things like rubber, wood, insulators, the lowest energy state is for the electrons to stay put. Okay, so I see another question. Layla is asking, how do you pronounce ampere? I do not want to sound weird saying it wrong. It's pronounced ampere, amp-ear. But if you don't want to sound silly, you can just say amps. Time for a Little Anarchy asks, is water flowing through a hose a good analogy for electric current? Yes, it is. All right. So what does electric current do to a material? Well, if you think about these electrons, the electrons are flowing and they're going to be bumping into atoms. So they're not just going straight through. They're going to be sort of pinballing. They're going to be going bing, 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 bing. The electrons are bouncing all over the place as they flow. And so as they bounce into the material, as they're flowing, they're going to cause the material to start jiggling. And that jiggling is represented as heat. So when electric current flows through something, the material heats up. This is basically what's happening in your toaster. In your toaster, electric current is shoved through those little wires on the sides of the toaster. It heats up the material. There's a good question. Okay, so Theo asks, is the ampere only equal to coulombs per second, or is it also equal to the electric current? So ampere is the unit of electric current, and 1 ampere is synonymous with 1 coulomb per second. Okay? How fast does electric current move? That's a really good question. So basically what happens is once the electrons start moving, they all start moving together. So it's like a river, okay? You know, you can imagine a river that's stationary and then the entire river just starts moving all at once. As far as the speed of the actual electrons, the electrons are bouncing around really fast, but I think I cut out for a second and I'm back. The other thing I wanted to say is that your brain signals to your body to do stuff with electric current. So if you're being electrocuted, the electric current is overriding the signal from your brain. The electric current is overriding the signal for your brain. So if you are being electrocuted, your hands, they might clench shut. And your brain is telling your hands to open. But your hands aren't listening to your brain anymore. They're listening to the electric current. So I apologize for the lag. I don't know what's happening. So anyways, if you're being electrocuted, or if your muscles will all tense up and you won't be able to untense them because the electric current is controlling your muscles, not your brain anymore. All right. So this is going a little bit longer than I wanted to, so I'm going to speed up a little bit. So key concepts so far: conductors, insulators, electric current. Okay. Next key concept is something called electric potential difference. Electric potential difference, which is also known as voltage. Okay. And electric potential difference is denoted by delta V. And it is a force that causes current to flow. Okay, so it's a force that causes current to flow. So what causes current to flow? Well, a good example of that would be batteries. So batteries provide a voltage. Batteries provide an electric potential difference. Another example would be the power outlet. So those all provide electric potential differences. The units of electric potential difference, delta V, are called volts, which is abbreviated by V. Okay. So, for example, batteries, a AA battery has 1.5 volts. It provides 1.5 volts of force. A car battery provides 12 volts. The power outlet is 120 volts. So different devices have different voltages. Okay, different forces. So you could think about the electric potential difference as the cause, and you could think about electric current as the effect. Okay? So electric potential difference causes electric current to flow. Ooh, we have a question here from Astrosloth. So does the voltage change the speed of the electron? Yes. So the larger the voltage is, the larger the voltage difference, the greater the speed that the electrons will have. Now, what does that mean in an actual material? It means that the electrons are going to go faster down the material. But really what that means is that when they bump into the atoms that are already present in the material, because you'll remember I said they don't go straight through, they bump into stuff. When they bump into stuff, they hit harder because of the greater potential difference, which means that the material heats up more. Okay? So yeah, that's an excellent observation. Okay, so what would it mean? So there's this thing called resistance, which is denoted by R, and it's equal to the potential difference divided by the amount of current that flows. Okay, so you can imagine. So this makes a whole lot of sense. I'm going to explain why this makes sense. What if you have a huge potential difference, but a very small current? That means you have a large force that's trying to make current flow, but not a lot of current is flowing. So you can imagine if you're trying really hard, but you're not getting much of a result, that must mean that it's a difficult thing, okay? So if this number is big and that number is small, then the ratio is going to be large, and that means a big resistance, okay? So alternatively, if you have a small delta V, a small potential difference, and a big current, that means you're hardly trying at all, but you're getting a huge result. So in that case, the material it's very easy for electric charge to flow through that material. Okay? So that's why this is called resistance. The units of resistance are, well, based on this, you can see, oh, I have a question over here. Let me answer the question. Does higher voltage mean more power? Yes, it does. Well, yes, it does mean more power. What is an example of resistance? That's another great question. Everything has a resistance. And if you were in class today, I have devices that measure resistance. And you can literally hold on to either end of the device and measure the resistance of your body. So everything has a resistance. If something is an insulator, it has a large resistance. If it's a conductor, it has a low resistance. So can current flow through an insulator? Yes, it's just not very much flows. So resistance is a property of a thing. I have another good question. If a battery has a higher voltage, does it last longer or is it just stronger? So AA batteries provide 1.5 volts. AAA batteries provide 1.5 volts. But a AA lasts longer than a AAA. All right? So sort of the physical size of the battery compared to its voltage determines how long it's going to last for. A D battery provides 1.5 volts, but it's really big, and so it's going to last the longest. Your TV remote, could you connect D batteries into your TV remote, which probably uses AAA batteries? Yes, you could. It provides the exact same voltage. The D battery would last a really long time in that application. But the reason that they don't use D batteries in TV remote controls is because they're large and heavy. Okay? So, it's a good question. So, resistance, units of resistance, we can see it's a potential difference divided by a current. So, its units would be volts per amp. Okay. Volts per amp. That has a special name as well. It's called the ohm, which is denoted by the Greek letter omega. Okay, so resistance is measured in ohms. All right, so I'm just about done for today. Tomorrow I'm going to give you some pretty sweet ohm puns, so look out for that. You'll get some ohm puns. That'll be fun. So what if I had a graph here of volts, or of current versus voltage, electric potential difference applied. This graph, it might look like a straight line. So what would the slope of this straight line mean? It would mean you have, I've got some good puns going on right now on the side. Ohm, I get it now. Very good, Will. Thank you. So the slope here would be, if we think about it, the current is the rise, and the volts are the run. So if I said slope is rise over run, it would be I over V. Well, if we look at resistance, resistance is V over I. Okay, so the slope is actually 1 over the resistance of this graph. Okay, so for example, if the slope was 5, then that would mean your resistance was 1/5 or 0.2 ohms. Okay, so I think that's all I'm going to go over today. And I look forward to talking to you tomorrow. So bye, everyone. Thank you for joining.